Far beyond the reach of ordinary sight, James Webb is looking deeper into the cosmos than ever before. But what it is finding is raising a disturbing possibility. Some of the earliest galaxies in the universe appear far too bright, far too massive, and far too mature to exist so soon after the beginning of time. If these observations hold, they may force science to confront a shocking question. Has James Webb uncovered evidence that our understanding of the universe is incomplete? Or something even more unsettling, that a very different universe may exist beyond what we thought was possible? Before we begin, make sure to like this video, subscribe to the channel, and turn on notifications for more deep space mysteries. The night sky extends in all directions as a quiet field of darkness, interrupted by points of light that have travelled across immense distances before reaching the Earth. Beyond the familiar stars of the Milky Way, the wider universe stretches outward into regions so distant that their light arrives faint and shifted, carrying with it a record of earlier cosmic conditions. In this outermost view, the structure of the universe appears not as a uniform glow, but as a vast web of matter, where galaxies gather in clusters and filaments separated by large, nearly empty spaces. Observations from ground and space-based telescopes over many decades have revealed this large-scale arrangement, showing that galaxies are not scattered randomly, but follow patterns shaped by gravity acting over billions of years. Light is the primary messenger from these distant regions. Every photon that reaches a telescope has travelled through expanding space, sometimes for billions of years, before being recorded. During this journey, the fabric of space itself stretches, and with it the wavelength of the light becomes longer. This process is known as redshift, and it provides a key method for understanding distance and time in the universe. The more distant a galaxy is, the more its light has been stretched, shifting it toward the red and infrared parts of the spectrum. This gradual change allows astronomers to arrange galaxies along a timeline, observing the universe not only across space, but also across its history. The observable universe is defined by the limit of how far light has had time to travel since the beginning of cosmic expansion. Beyond this boundary, regions may exist but remain unseen because their light has not yet reached any observer. Within this observable region, astronomers study galaxies at many stages of development, from nearby systems rich in detail to distant ones that appear as faint points or blurred shapes. These distant galaxies are especially important because they offer glimpses of the early universe, when matter first gathered into stars and larger structures. In the outermost view, time and distance are closely linked. Looking farther into space means looking further back in time. A galaxy seen at a great distance is observed as it was long ago, not as it is now. This connection transforms the sky into a layered record, where different depths correspond to different epochs. The earliest light that can be observed comes from a time when the universe was much younger, when stars were just beginning to form and galaxies were still assembling. These earlier stages are difficult to study because the light is extremely faint and has been stretched far into longer wavelengths. To explore these distant regions, astronomers rely on instruments capable of detecting very faint signals. The sensitivity of a telescope determines how much light it can collect, while its resolution defines how clearly it can distinguish small details. Over time, improvements in both sensitivity and resolution have allowed deeper exploration into the cosmic past. Space-based observatories avoid the distortion and absorption caused by the Earth's atmosphere, enabling clearer and more complete measurements of distant light. The distribution of galaxies across the sky reveals patterns that reflect the influence of unseen matter. Observations indicate that most of the mass in the universe does not emit light and is therefore invisible to direct detection. This component, known as dark matter, shapes the formation of galaxies by providing gravitational structure. Ordinary matter, composed of atoms, falls into regions where dark matter is concentrated, leading to the formation of stars and galaxies over time. This interplay between visible and invisible matter is a central feature of the large-scale universe. As light travels through space, it may pass near massive objects such as galaxy clusters. The gravity of these objects can bend the path of light, an effect described by general relativity. This bending, known as gravitational lensing, can magnify or distort the appearance of distant galaxies. In some cases, it allows astronomers to observe objects that would otherwise be too faint to detect. These natural lenses provide a way to extend the reach of observation even further into the distant universe. The outermost regions accessible to observation are not sharply defined but gradually fade into uncertainty. As distance increases, signals become weaker and more difficult to interpret. Noise from detectors, interference from closer objects, and the limits of instrument sensitivity all contribute to the challenge. Despite these difficulties, careful analysis allows astronomers to extract meaningful information from faint light, building a picture of the early universe piece by piece. Over many years, a consistent framework has emerged to describe the large-scale behavior of the universe. This framework includes the idea that space is expanding and that galaxies are moving away from one another on average. The rate of this expansion can be measured through observations of distant objects and their redshift. While this general picture is widely supported, details continue to be refined as new data become available. In this vast outer region, the universe appears calm and structured on the larger scales, yet filled with subtle variations that carry important information. Small differences in brightness, color, and shape among distant galaxies provide clues about their composition, age, and history. By studying these details, astronomers attempt to reconstruct the sequence of events that led from a nearly uniform early state to the complex structures seen today. The quiet darkness of space, when observed with sensitive instruments, reveals a rich and evolving environment. Each faint point of light represents a galaxy containing billions of stars, each contributing to the overall glow. Together, these distant systems form a tapestry that records the passage of cosmic time. The study of this outermost region sets the stage for deeper investigation, guiding attention toward the tools and methods used to capture such faint signals. As observation pushes further into distance and time, the need for more advanced instruments becomes clear. The faintest galaxies require not only large mirrors to collect light, but also detectors tuned to the longer wavelengths where ancient light now resides. The effort to observe these distant objects leads naturally to the development of specialized telescopes designed for this purpose. Far from the surface of the Earth, beyond the crowded paths of low-orbiting satellites, and well beyond the height where the atmosphere fades into near vacuum. The James Webb Space Telescope moves with quiet steadiness through a region of space chosen for balance rather than closeness. It does not circle the Earth in the familiar way that many earlier observatories do. Instead, it remains near a special location in the Earth and Sun system known as the second Lagrange point. A Lagrange point is a place where gravity and orbital motion combine in a way that allows a spacecraft to stay in step with the Earth as both move around the Sun. This particular region lies about 1,500,000 kilometers from the Earth, in the direction away from the Sun. From there, the telescope travels around the Sun alongside the Earth while keeping the Sun, the Earth, and the Moon on roughly the same side of its structure. This distant placement serves a clear purpose. The telescope is built to study very faint infrared light, and infrared light is closely related to heat. any warm object glows in infrared wavelengths. The Earth glows, the Moon glows, the Sun radiates enormous energy. A telescope that tries to measure dim ancient infrared signals cannot work well if it is surrounded by nearby warmth. At the second Lagrange point, the observatory can keep its hot surroundings grouped together in one direction and shield itself from them. This arrangement helps create a stable thermal environment, and thermal stability is essential for precise measurement. The telescope is not cold by accident. It is cold because its scientific purpose requires coldness as a condition of seeing. The observatory does not rest exactly on the second Lagrange point as though it were a fixed platform in space. Instead, it follows a wide looping path around that region. This gentle orbit allows the spacecraft to avoid passing through deep shadow from the Earth, while maintaining a clear view of space and a stable orientation for communication and power. The path is carefully managed through small adjustments, because space is quiet but never passive. Gravity continues to act. Sunlight exerts pressure, and even a small drift matters when sensitive observation depends on alignment. The shape of the telescope reflects its purpose immediately. Its most visible feature is a broad primary mirror made from 18 hexagonal segments joined into one large collecting surface. Together they form a mirror about 6½ meters across. The mirror is large because distant cosmic light is scarce. To observe faint galaxies from the early universe, the telescope must gather as many photons as possible. A larger mirror collects more light, improving sensitivity and allowing objects too dim for smaller instruments to emerge from darkness. The segmented design makes it possible to build a mirror much larger than a single rigid piece could easily be launched. Each segment is carefully positioned and adjusted with extreme precision so that all parts act together as one optical surface. The mirror is made from beryllium, a metal chosen because it remains stable across a wide range of temperatures and performs well in the cold conditions of space. Each segment is coated with a thin layer of gold. The gold is not decorative. It improves the reflection of infrared light, which is the part of the spectrum the telescope is designed to study. When faint light from distant space reaches the mirror, it reflects toward a smaller secondary mirror held above the main surface by a tripod-like support structure. From there, the light is directed into the scientific instruments, where it can be measured, separated by wavelength, and recorded. Beneath the mirrors lies one of the most important structures on the entire observatory, the sun shield. It spreads out in several thin layers and is about the size of a tennis court. These layers work together to block heat and light from the sun, the Earth, and the Moon. The side facing the sun becomes much warmer, while the telescope side remains deeply cold. Each layer is shaped and spaced so that heat radiates outward rather than passing directly through. This shield is not simply a covering. It is an active part of the observatory's ability to function. Without it, the telescope itself would glow too strongly in infrared light and overwhelm the very signals it is meant to detect. The telescope carries several scientific instruments, each designed for a particular kind of measurement. One instrument is optimized for imaging in the near-infrared, allowing the observatory to record sharp pictures of distant galaxies, stars, and nebulae. Another performs spectroscopy, which is the splitting of light into its component wavelengths. Spectroscopy reveals chemical composition, temperature, motion, and other physical properties. A third instrument combines imaging and spectroscopy in the near-infrared and allows many targets to be studied efficiently. There is also an instrument that observes at mid-infrared wavelengths, extending the telescope's reach to even longer light. Because this instrument works at wavelengths especially sensitive to heat, it requires additional cooling beyond the passive cold provided by the sunshield. A cryocooler, a machine designed to remove heat, keeps it cold enough for accurate observation. Each instrument contributes to a broader method of study. The observatory does not merely take pictures in the ordinary sense, it measures light with care, often across different wavelength bands, so that astronomers can infer distance, age, composition, and structure. A galaxy that appears as a faint reddish mark in one image may reveal through spectroscopy the presence of ionized gas, dust, or newly forming stars. A star hidden within a dusty cloud may appear clearly in infrared light even when visible light is blocked. The telescope functions as a collector, a separator, and a translator of light. Its location also supports reliable observing, because the Sun, Earth, and Moon remain on the same general side of the telescope. The spacecraft can keep its solar panels facing the light source needed for power, while the mirrors and instruments face the darkness needed for science. Communication with Earth is maintained through planned contact windows, and the observatory can point toward different regions of the sky over time without losing the thermal arrangement that preserves its sensitivity. This geometric order is one of the hidden strengths of the mission. The telescope is not only a mirror in space, it is a carefully balanced system in which orbit, temperature, pointing, and instrument design all serve one another. Before scientific observations begin, the telescope undergoes alignment and calibration. Light from stars is used to adjust the mirror segments until they act as one surface, bringing images into precise focus. This process demands extraordinary care because even tiny mismatches would blur the data. Once aligned, the telescope achieves resolution and sensitivity that allow extremely faint structures to be studied in detail. It can observe some of the earliest galaxies yet detected, peer through dusty stellar nurseries, and analyze the atmospheres of planets around other stars. All of this depends first on where it is and how it is built. In its distant orbit, the observatory remains quiet, cold, and deliberate. It floats in darkness with one side turned toward warmth and one side turned toward the deeper sky. Every major feature of its design answers a single need to gather ancient faint infrared light without drowning it in nearer heat. The telescope's remote station, its shield, its golden mirror, and its cooled instruments form one continuous arrangement. In that arrangement, the outer machinery of discovery holds still long enough for distant light to arrive and be read. Infrared light moves through the universe as a quiet extension of the visible spectrum, lying beyond the deep red edge that human eyes can detect. It is still light, still part of the same electromagnetic family, but it carries longer wavelengths and often comes from conditions that visible light cannot show clearly. In the wide outer regions of space, this matters greatly. Dust drifts between stars and galaxies, thin by earthly standards but widespread enough to block and scatter shorter wavelengths. Visible light is easily interrupted by these grains. Infrared light passes more readily through them. Because of this, regions that appear dark or hidden in ordinary images often become clear when viewed in infrared. The effect is not magical. It arises from the interaction between light and matter, where longer wavelengths are less strongly scattered by small particles. This property makes infrared observation especially valuable in astronomy. Large clouds of gas and dust lie throughout galaxies, including the Milky Way, and within those clouds stars are born. In visible light, these star-forming regions may seem sealed behind opaque curtains. In infrared, the curtain becomes thinner and deeper layers can be observed. The same principle applies on larger scales. Galaxies rich in dust may conceal much of their internal structure when viewed only in visible wavelengths. Infrared light can reveal stars, warm dust, and active regions that would otherwise remain partly obscured. In this way, infrared astronomy opens a wider set of windows into the universe, allowing hidden processes to be studied more directly. Infrared also becomes essential because of cosmic expansion. As space expands, light traveling through it is stretched to longer wavelengths. A photon that leaves a distant galaxy in ultraviolet or visible light may arrive billions of years later shifted into the infrared. This stretching is redshift. It does not mean the light has passed through red color on a palette in any ordinary sense. It means the spacing between wave crests has grown during the journey. The greater the distance and the earlier the cosmic time from which the light comes, the stronger this effect tends to be. For the most distant known galaxies, much of the light that began in shorter wavelengths now reaches observers as near-infrared or even mid-infrared radiation. Because of this, the early universe is not best searched for in visible light alone. Ancient galaxies can be missed if instruments are blind to the wavelengths where their stretched light now resides. This is one reason the James Webb Space Telescope is built around infrared sensitivity. It is designed not simply to look farther, but to look where the old light has moved. The deepest past visible to astronomy is not hidden only by distance, it is hidden by wavelength. To detect it, an observatory must be able to receive the long, faint light that has crossed expanding space since the first generations of stars and galaxies began to shine. Infrared observation, however, comes with strict demands. Because warm objects emit infrared radiation, the telescope itself can become a source of interference. A mirror, detector, or support structure that is too warm adds its own glow to the measurement. For this reason, infrared astronomy depends on cooling, shielding, and careful detector design. When these conditions are achieved, faint cosmic signals can be separated from local heat. The result is not only a clearer image but a more faithful record of distant conditions. A dim galaxy from the early universe may contribute only a very small number of photons, and those photons must be distinguished from everything nearby that might imitate them. Within infrared astronomy there are different ranges. Near-infrared lies closer to visible red light and is especially useful for studying distant galaxies, stars, and the red-shifted glow of early cosmic structures. Mid-infrared reaches longer wavelengths and becomes valuable for examining cooler dust, certain molecules, and thermal emission from objects that are not hot enough to shine strongly in visible light. Together, these ranges allow astronomers to move across different physical environments: hot young stars, dusty stellar nurseries, old red stars, and remote galaxies. Each leaves signals that can be traced in one part of the infrared spectrum or another. The detectors that measure infrared light do not work by simple photography in the ordinary sense. They convert incoming radiation into electrical signals that can be counted, compared, and mapped. These detectors must be highly sensitive and exceptionally stable. Noise, which is unwanted signal from the instrument or its environment, can easily obscure faint sources. Astronomers reduce noise through cooling, repeated observations, calibration, and statistical methods that distinguish real object from random fluctuations. In deep surveys, the same region of sky may be observed for many hours so that weak signals gradually rise above the background. This patience is a key part of how very distant galaxies are found. Infrared data also help astronomers estimate physical properties. The color of an object across several infrared bands can suggest its redshift, the presence of dust, and the age distribution of its stars. When infrared light is dispersed through spectroscopy, dark and bright features appear that correspond to atoms and molecules interacting with radiation. These spectral features can indicate the presence of hydrogen, oxygen, carbon, and other elements, along with gas motion and temperature. In the case of distant galaxies, such measurements help determine whether a source truly belongs to the early universe or only resembles it in color because of dust or some nearer effect. This creates both power and caution. Infrared windows allow deeper access to ancient light, but interpretation remains delicate. A faint red object may indeed be a galaxy from the young universe whose light has been strongly stretched. It may also be a nearer object with heavy dust, or a source whose brightness is affected by lensing, detector noise, or overlap with neighboring light. Observations indicate that infrared surveys are extremely effective at identifying candidate distant galaxies, yet it remains uncertain in many cases until spectroscopy confirms the distance. In astronomy, seeing deeper does not remove ambiguity by itself. It changes the available evidence and often improves the chances of correct interpretation, but the evidence still requires careful handling. The opening of infrared windows has changed the map of the sky. Regions once considered blank become populated with sources. Dusty lanes become partly transparent. Ancient galaxies emerge from wavelengths where earlier instruments had only limited reach. The universe does not become more crowded in reality, it becomes more legible. Patterns once hidden by material or by redshift begin to take shape as data points, images, and spectra. Each new detection depends on the long journey of stretched light and on instruments tuned precisely to receive it. In this outer layer of the subject, infrared light acts as the bridge between the remote universe and human measurement. It carries the record of dust-veiled environments and very distant epochs into detectors built to read long wavelengths with care. It reveals not another realm separated from known physics, but a wider and older portion of the same cosmos, rendered visible by choosing the right window. Through that window, astronomers begin to examine particular regions of sky where ancient light gathers in deep survey fields and where the first strong hints of cosmic surprise begin to appear. The first survey fields observed by the James Webb Space Telescope are not chosen at random. They are small regions of sky selected with care, often because earlier observatories have already studied them deeply and built a foundation of measurements around them. In the immense darkness of the wider universe, these fields are like patiently examined windows. They are narrow compared with the whole sky, yet they are rich in information because astronomers return to them again and again with better instruments. By concentrating light collection on these limited regions, Webb turns tiny patches of apparent emptiness into densely populated records of cosmic history. One of the earliest and most widely recognized of these fields is the region around the galaxy cluster SMACS 0723. This field becomes famous because it serves as Webb's first deep field image. The cluster itself lies much nearer than the most distant galaxies visible behind it, and its large mass bends light from more remote objects through gravitational lensing. This effect magnifies background galaxies and allows faint structures to appear more clearly than they otherwise would. The field is not only deep because Webb observes it with great sensitivity, it is also deep because nature assists the observation by providing a cluster massive enough to act as a lens. In a small patch of sky, thousands of galaxies become visible, some belonging to the foreground cluster and many far behind it, their light stretched and bent on its way to the telescope. The selection of such a field reflects a practical scientific strategy. Astronomers do not simply want beautiful images. They want regions where every photon can serve several purposes at once. A cluster lensing field can reveal the properties of the cluster itself, the distribution of dark matter through lensing patterns, and the magnified light of distant galaxies from the early universe. This makes each exposure especially valuable. The field around SMAC 0723 is therefore both a demonstration and a working laboratory. It shows what Webb can do, but it also begins the more serious task of measuring objects near the edge of current observation. Other fields are chosen not because a foreground cluster magnifies them, but because they are already among the most carefully mapped areas of the sky. One important example is Goods South, a region observed by many previous telescopes across many wavelengths. The name refers to the Great Observatory's Origins Deep Survey, a long effort to build a layered view of distant galaxies using several instruments, because so much is already known there. Webb can enter the field not as the first explorer but as a much more powerful successor. Earlier imaging, source catalogues, and measurements of known objects create a context in which new, infrared detections can be compared, checked, and interpreted more reliably. Within this region, the JADES program, the JWST Advanced Deep Extragalactic Survey, becomes especially important. JADES is designed as a major deep survey of distant galaxies, using both imaging and spectroscopy to identify and study sources in the early universe. The value of such a program lies in its combination of depth and method. Webb does not merely glance at the field, it collects enough light to reveal very faint candidate galaxies, then uses spectral measurements to test whether their apparent great distance is real. In this way, the field becomes more than an image. It becomes a structured investigation, where points of light are sorted into likely nearby sources, dusty intermediate objects, and genuinely remote galaxies whose light has travelled from very early cosmic time. The Hubble Ultra Deep Field and nearby surrounding regions also remain important in the Webb era. These are classic deep fields first made famous by earlier space observations that showed how even a seemingly blank patch of sky contains a vast number of galaxies. Webb revisits such regions with infrared instruments that can see older and more distant light than Hubble could capture with the same depth. The field is therefore familiar and new at once. Astronomers already know its broad contents. Yet Webb changes the texture of the view. Galaxies that once appeared as faint smudges begin to show internal structure. Red sources that once stood at the edge of certainty become stronger candidates for extreme distance. Dust-hidden features become clearer. In a field where the sky has been studied for years, Webb adds not breadth but penetration. Survey fields are also selected for technical reasons. Astronomers prefer regions where foreground stars from the Milky Way are not too crowded. Since too many nearby stars can complicate the detection of faint galaxies in the background, they also seek regions with low levels of interfering dust from our own galaxy. A clean line of sight matters, even though infrared can pass through dust more easily than visible light. Less foreground contamination still improves measurement. Some fields are located near the ecliptic poles or other convenient regions that allow extended observation windows. In such places, Webb can stare longer with fewer interruptions, which is essential when the goal is to collect the weaker signals from the farthest sources. These survey regions may seem small when described in angular size. A deep field can cover an area that appears tiny against the whole dome of the sky, sometimes compared with a grain of sand held at arm's length. Yet within that narrow view, the number of galaxies can be extraordinary. This is one of the recurring lessons of deep observation. Emptiness is often only the result of limited sensitivity. when exposure time increases and the right wavelengths are observed, the dark field fills with structure. Each point or faint arc may correspond to a galaxy containing millions or billions of stars. The apparent emptiness of the outer sky gives way to abundance once observation becomes patient enough. The first survey fields therefore function as test grounds for a larger question. If Webb can detect many distant galaxies in carefully chosen windows, then astronomers can begin to ask how numerous early galaxies are, how bright they tend to be, how quickly they grow, and how their light contributes to the transformation of the young universe. The field itself remains the current region of attention. At this stage, the focus is not yet on final interpretation, tension, or dramatic theory. It is on the act of gathering the light in places most likely to reward careful looking. Every chosen field is a compromise between sky position, previous knowledge, observational efficiency, and scientific ambition. Some are lensing fields shaped by the gravity of massive clusters. Some are legacy fields enriched by decades of earlier observation. Some are selected because their geometry and cleanliness allow exceptionally deep exposures. Together they form the first map of where Webb begins its deepest search. These are the narrow portals through which astronomers look outward and backward at once, trusting that in these tiny areas the ancient universe can be sampled with unusual clarity. By concentrating on these fields, Webb turns selected darkness into evidence, and the evidence begins as a population of faint galaxies waiting to be described. Within the first survey fields, the most arresting features are often not the largest galaxies or the brightest foreground stars, but the faint distant sources whose light appears unexpectedly strong for such an early time. These early galaxy candidates do not arrive as fully explained objects. They first appear as points, patches, arcs, and reddish forms set among countless others in the deep images. Their importance emerges gradually. In the outermost layers of interpretation, astronomers begin by describing what is plainly their brightness, colour, size, symmetry, compactness, and the presence or absence of visible internal structure. Before any large claim is made, the light itself is examined as carefully as possible. Many of these distant candidates appear red in the Webb images, not because they are necessarily red in their own local setting, but because the expansion of space has stretched their light toward longer wavelengths before it reaches the telescope. In the selected infrared bands, they stand out by becoming visible in some filters and nearly absent in others. This pattern is often the first clue that a source may lie at very great distance. At the level of appearance, the effect is simple. A galaxy seems to emerge where shorter wavelength observation shows little or nothing. It is as though the object steps into view only when the telescope looks with the proper kind of light. That sudden appearance in long wavelength bands becomes one of the visual signatures that draws attention to the earliest candidate galaxies. Their brightness is one of the first surprises. Under earlier expectations, galaxies at very early cosmic times were often imagined as small, irregular, dim systems, still in the first stages of assembly. Yet some of the Webb sources look more luminous than this simple picture would suggest. They do not all appear weak and barely present. Some show enough light to imply a substantial population of stars, vigorous star formation, or some combination of both. The images alone do not settle which explanation is correct, but they do create a strong impression that the early sky may contain more conspicuous galaxies than expected in at least some survey regions. Their shapes also attract attention. A number of these candidate early galaxies appear compact, meaning their light is concentrated into a very small region on the sky. Compactness by itself does not tell the whole story, because great distance naturally reduces apparent size. Still, Even after allowing for that effect, some sources seem dense and organized rather than diffuse. Others show hints of elongated or clumpy structure, suggesting regions of active formation or merging components. In a few cases, the appearance is unexpectedly smooth, giving the impression of a system whose stars are already gathered into a fairly settled shape. Observations indicate that early galaxies can display more variety than a simple first-generation picture might suggest. Some look uneven and fragmentary, while others seem more mature in profile. Color adds another layer to their outer appearance. In deep-field images, astronomers combine data from different wavelength bands to produce color representations that help separate objects by their light profiles. Very distant galaxy candidates often occupy a distinctive range in these composites, standing apart from many nearer galaxies and stars. Yet color is always a clue rather than a verdict. Dust within a nearer galaxy can also redden its light. A faint source affected by measurement uncertainty can appear more extreme than it truly is. For this reason, the first descriptions remain careful. Astronomers note that a source is bright, red, compact, or structured, but they do not rely on any single visual quality alone. Appearance begins the process. It does not complete it. Some of the strongest early reactions to Webb data come from the impression that certain galaxies look too substantial too soon. This impression arises first at the visible surface of the evidence, in the deep images themselves. When a source appears bright enough to suggest many stars, and when its shape seems more organized than expected, the eye immediately senses attention even before detailed analysis begins. The images do not announce a new universe. They present a quieter and more disciplined challenge. They show light patterns that appear, at least on first inspection, to fit uneasily with simplified expectations about how quickly galaxies should have grown in the earliest eras. At this stage, astronomers also pay attention to the environment around these sources, nearby objects, foreground contamination, and gravitational lensing can all alter how a galaxy appears. A distant source close to a bright neighbor may have its light blended in a way that exaggerates or distorts its apparent form. A lensed object may appear brighter or stretched into an arc. Instrumental effects can also shape the recorded image, especially when dealing with extremely faint points near the edge of detection. Thus, the outer appearance of a candidate galaxy is never taken as a simple photograph in the everyday sense. It is a measured image shaped by optics, detectors, cosmic geometry, and data processing. Even so, the recorded forms remain real evidence, and they are the first basis for scientific description. The deep-field images reveal that early galaxies are not all alike. Some are so faint that they remain near the limit of visibility, with only a small cluster of pixels announcing their presence. Others are clearer and more stable under repeated analysis. A few appear in groups or crowded neighborhoods, hinting that galaxy gathering and interaction may already be underway in the early universe. This diversity matters. It suggests that early cosmic history is not made of one standard object repeated many times, but of a range of systems developing under slightly different local conditions. Even the outer layer of the evidence, before deeper measurement, points toward complexity. There is also an emotional discipline built into this kind of work. The images are striking, but the scientific habit remains restrained. A luminous source at great distance may indeed represent an unexpectedly evolved galaxy. It may also turn out, after more careful study, to be less distant, less massive, or differently understood than first thought. The appearance of maturity can come from intense, short-lived star formation, rather than long-settled development. Brightness can reflect a burst rather than a vast accumulated history. structure can seem stronger in processed images than in raw data. For these reasons, astronomers describe what is seen with precision, but resist turning first impressions into final conclusions. In these early galaxy light fields, the outer evidence is therefore both simple and profound. Webb reveals points and patches of ancient light that are red, compact, and in some cases unexpectedly bright. It shows faint galaxies beginning to separate from darkness with enough clarity to raise careful scientific unease. The first layer of surprise lies not in a theory, but in the visible character of the sources themselves, their glow, their shapes, and their seeming degree of development begin to press against prior expectations. The images remain quiet, but the quiet contains a challenge. In the deep survey fields, ancient galaxies do not merely appear, they arrive with a look that demands closer measurement, especially in the way their light has shifted across the expanding universe, and in how that shift is used to place them in cosmic time. Redshift and distance form one of the central links between the deep sky and cosmic history. Once a faint galaxy appears in a survey field and its outer light has been described, astronomers ask where it belongs along the long timeline of the universe. The answer does not come from ordinary depth perception, because the sky offers no simple visual scale for such remote objects. A distant galaxy is not measured by how far away it seems to the eye. It is placed through the behavior of its light. As that light crosses expanding space, its wavelength becomes longer. This stretching shifts it toward the red and infrared parts of the spectrum, and the amount of that shift provides a way to estimate how far back in time the galaxy is being seen. A wavelength is the distance from one crest of a light wave to the next. When space expands during the journey of light, that spacing grows. The light is not merely dimmed by travel. Its pattern is altered by the expansion of the universe itself. This is redshift, in a broad sense. The higher the redshift, the earlier the epoch from which the light comes. The relationship is not interpreted as a simple speed through empty space in the everyday sense. It belongs to cosmology, where expanding space changes the scale through which light moves. Because of this, redshift becomes a bridge between an observed signal and a place on the cosmic timeline. Astronomers often describe redshift with a number that expresses how much the wavelength has been stretched, compared with its original emitted form. A galaxy with a larger value is generally being seen from a younger period of the universe than a galaxy with a smaller one. This does not mean every aspect of distance can be reduced to one easy measure, because cosmological distance itself has several forms. There is the travel time of the light, the present separation that would exist if expansion is taken into account, and the way brightness changes with geometry across the expanding universe. Yet for deep field work, redshift provides the first essential ordering principle. It tells astronomers whether a source belongs to the nearby universe, the more mature middle eras of galaxy growth, or the much earlier periods when galaxies are only beginning to assemble. There are two main ways to estimate the redshift of a distant galaxy. The first is photometric redshift. This method uses images taken through several filters, each sensitive to a different range of wavelengths. A very distant galaxy may vanish in shorter wavelength bands and then appear in longer ones. This sudden change can mark the point where intergalactic hydrogen absorbs light below a certain wavelength. As redshift increases, that boundary moves through the filter set. By measuring the pattern of brightness across the filters, astronomers can estimate where the object likely sits in redshift. Photometric redshift is efficient and powerful, especially when large numbers of faint galaxies must be surveyed. It allows candidate early galaxies to be identified even when they are too faint for immediate detailed spectroscopy. The second method is spectroscopic redshift. This is more precise when it can be obtained. In spectroscopy, the light from a source is spread into a spectrum, and astronomers search for identifiable features, such as emission lines or absorption features connected to known atomic processes. If one of these features is found at a shifted wavelength, the amount of shift can be measured directly. This provides a firmer determination of a redshift than color patterns alone. Spectroscopy is therefore especially valuable in confirming whether a candidate galaxy truly lies in the early universe. It turns a likely distance into a more secure one. The difficulty is that extremely remote galaxies are faint, and their spectra may be weak or incomplete. Even with Webb, confirmation can demand long exposure times and careful analysis. Once a redshift is estimated, astronomers translate it into cosmic time using the standard model of expansion. This model includes the effects of matter, dark matter, and dark energy on the changing rate of expansion across the history of the universe. Because expansion has not proceeded at one constant rate, the relation between redshift and time is not linear. A difference in redshift at low values does not correspond to the same change in age as a similar difference at very high values. In the early universe, small shifts in redshift can move a galaxy across significant intervals in cosmic development. This is why careful measurement matters so much. If a faint object is placed too early, it may appear to challenge expectations more strongly than it truly should. If it is placed too late, its importance for early structure formation may be understated. Brightness is often discussed alongside redshift, but the two are not the same. A high redshift galaxy can appear bright for several reasons. It may contain a large number of young hot stars. It may be undergoing an intense burst of star formation. It may be magnified by gravitational lensing, or it may be affected by interpretation choices about dust and stellar populations. Distance by itself tends to reduce apparent brightness. Yet some early sources still shine strongly enough to attract attention. This is where redshift becomes crucial. Without knowing how far back the galaxy is being seen, brightness has no clear meaning. A bright nearby object is ordinary. A bright object at extreme redshift can become a puzzle. Even with strong methods, uncertainty remains part of the process. A dusty galaxy at lower redshift can sometimes imitate the colors of a more distant source. Noise can distort the measured brightness in one filter and make a candidate seem more extreme. Overlapping light from neighboring objects can confuse the signal. Observations indicate that many photometric candidates hold up well under further study. Yet it remains uncertain for some sources until spectroscopy provides stronger evidence. This uncertainty is not a flaw in the method. It is a natural feature of working near the limit of detection, where astronomers must distinguish between faint realities and plausible imposters. Redshift also changes how astronomers think about the appearance of galaxies. A galaxy observed at very high redshift is not being seen after billions of years of quiet evolution. It is being seen during an early stage, when stars may be forming rapidly, gas may be unsettled, and structure may still be gathering. Thus, when a source is placed at extreme redshift, its apparent brightness or organization takes on greater significance. It is no longer just a distant galaxy. It becomes a galaxy seen at a surprisingly early moment. The deeper into cosmic time it is placed, the more its properties matter for models of early growth. In this region of the subject, redshift serves as the measuring thread that ties faint infrared light to the age of the universe. It orders the deep field sources along a timeline and gives meaning to their brightness, color, and form. Distance is not read from shape or from ordinary vision, but from stretched wavelengths and carefully interpreted spectra. Through this method, ancient galaxies are placed into cosmic history, and the early survey fields begin to look less like collections of faint marks and more like records from distinct eras. Once those records are arranged against the standard timeline of cosmic expansion, their significance becomes sharper, and the larger framework of accepted cosmology enters the foreground. The standard cosmological picture provides the broad framework within which these distant galaxies are understood. After faint light is gathered from deep survey fields and placed along the timeline through redshift, astronomers interpret those observations against a model that has been built over many decades from many independent lines of evidence. This model does not describe every detail of every galaxy, but it offers the large structure within which galaxies form, grow, and change. It describes an expanding universe that begins in a hot, dense early state, cools over time, and develops increasing structure as gravity gathers matter into larger systems. Within this picture, the earliest galaxies are not isolated surprises. They are expected outcomes of long physical processes acting under known laws, though the exact pace and pattern of their growth remain areas of active study. In this framework, the early universe begins in a nearly uniform state, with matter and radiation distributed very evenly but not perfectly so. Tiny variations in density are present from the beginning. These small differences matter greatly. Regions that are slightly denser than average exert a little more gravity, drawing in more matter as time passes. Over immense spans of time, these small beginnings lead to larger structures. Gravity turns slight unevenness into a cosmic network. Matter gathers into filaments and knots, and galaxies emerge within the deepest wells of this growing structure. This is the broad explanatory setting for why the deep sky is patterned rather than smooth. A central element in this model is dark matter. Dark matter is a form of matter inferred from its gravitational influence rather than from emitted light. Observations of galaxy rotation, gravitational lensing, cluster dynamics, and the large-scale structure of the universe all support the view that most matter does not shine. In the standard picture, dark matter begins shaping structure early because it is not strongly affected by radiation in the way ordinary matter is during the young hot phases of the universe. It forms gravitational scaffolding, and ordinary matter later falls into these dark matter halos. Gas cools, becomes denser, and eventually forms stars. Galaxies arise inside these halos, growing through continued gas inflow, star formation, and merging with other systems. Ordinary matter follows a more complex path. In the early universe, it is tightly linked to radiation and does not collapse freely at first. As the cosmos expands and cools, conditions change, allowing atoms to form and light to travel more freely. Later, gas settles into the dark matter framework and becomes available for star formation. This process does not happen everywhere at once. Some regions gather gas more efficiently than others. Some halos are more massive. Some environments favor rapid cooling. As a result, the first generations of stars and galaxies appear unevenly across space, and the early universe becomes a patchwork of regions at different stages of development. The standard model also includes the idea of dark energy, a term used to describe the observed accelerated expansion of the universe at later times. Dark energy affects the large-scale history of expansion, and therefore enters the relationship between redshift and cosmic time. It does not directly explain the small-scale details of early galaxy assembly, yet it remains part of the overall cosmological framework because it shapes how distances and times are calculated across the full history of the universe. In the era of the first galaxies, matter plays the dominant role in structure growth, but the larger model includes both matter and dark energy as essential components of cosmic evolution. Within this accepted picture, galaxies are expected to grow gradually, though not always smoothly. Gas falls inward, stars form, heavy elements are created, and explosive stellar deaths return energy and material to surrounding gas. This feedback can regulate future star formation. Small galaxies merge into larger ones, clumps form and disperse. Radiation from young stars alters nearby gas. Black holes may begin to grow in dense centers. The early universe is therefore active and irregular. But the overall expectation is that truly massive or highly evolved galaxies should be less common at very early times than at later ones. There has simply been less time for matter to gather, cool, form stars, recycle material, and assemble into large settled systems. This expectation does not mean the model predicts a simple ladder with one galaxy type per era. Even in the standard framework, some early galaxies can be brighter, denser, or more rapidly forming stars than others. Cosmic variance, which means natural variation from one region of space to another, can produce survey fields richer or poorer in luminous objects. Mergers can accelerate growth. Efficient star formation can produce impressive brightness in relatively compact systems. Thus, the model already allows diversity. What it provides is not a rigid image of one early galaxy shape, but a statistical sense of what should be common, what should be rare, and how population should shift over time. The chemistry of the universe also develops within this framework. The earliest matter is mostly hydrogen and helium, with only traces of other light elements formed in the young cosmos. Heavier elements are made later inside stars and dispersed by stellar winds and explosive deaths. This means the first galaxies are expected to begin with chemically simple gas, and only gradually enrich their surroundings. The amount of dust, the cooling efficiency of gas, and the nature of early star formation all depend in part on this chemical history. When astronomers examine distant galaxies with Webb, they're not only asking how bright the galaxies are, they're also asking how much chemical change may already have occurred by the time the observed light is emitted. The standard cosmological model has strong support because many observations agree with it at once. The large-scale distribution of galaxies, the properties of the cosmic microwave background, the abundance of light elements, and the general history of expansion all fit within a shared mathematical description. Yet the model is strongest at the level of broad structure and statistical behavior. The formation of individual galaxies remains more difficult to predict in detail. Because many interacting processes shape them, gas cooling, turbulence, star formation efficiency, stellar feedback, black hole activity, and merging histories all influence the final result. For that reason, early Webb observations test not only the large framework but also the astrophysical assumptions built inside galaxy formation simulations. This is where the baseline becomes important. When astronomers say that certain Webb results appear surprising, the surprise is measured against this standard picture. The model provides the timetable, the expected distribution of halo masses, the rough pace of galaxy buildup, and the predicted abundance of bright objects at different epochs. If galaxies appear more luminous, more massive, or more chemically developed than expected, then either the observations need reinterpretation, the astrophysical details within the model need adjustment, or some more fundamental ingredient may require rethinking. The framework itself is therefore not merely background. It is the reference against which tension becomes visible. In this region, the accepted cosmological view remains calm, broad, and structured. It describes a universe that grows from small density variations into a web of galaxies shaped by dark matter, gas physics, star formation, and expansion across cosmic time. It allows richness and irregularity, but it also sets expectations about what should be easy or difficult to build in the earliest eras. Once Webb's distant galaxies are compared against this shared baseline, the question changes. The issue is no longer only what is seen in deep fields or how far away the sources are. The issue becomes whether the observed early galaxies fit comfortably within the standard timeline, or whether some part of that timeline begins to feel strained under the weight of the new light. The tension appears only after the standard picture is used as a measuring frame. Once faint galaxies in the deep survey fields are given estimated redshifts, and once their brightness and apparent structure are compared with expectations from accepted cosmology, some of them begin to stand out. The issue is not that Webb sees distant galaxies at all. Those galaxies are expected. The issue is that a number of candidates seem, at first analysis, brighter, more massive, or more developed than simple versions of the timeline appear to allow with ease. The feeling of strain does not emerge from a single image or one isolated object. It grows from repeated encounters with sources that seem to occupy an unexpectedly strong place in the young universe. This strain is often described in careful statistical terms rather than dramatic ones. In the standard framework, the earliest eras should contain galaxies that are still assembling from smaller components, drawing in gas, forming stars quickly in some cases, and merging over time. Some luminous systems are possible, but they are expected to be less common as observation reaches back toward the first few 100 million years of cosmic history. When Webb begins to identify multiple candidates that appear very bright at these early times, astronomers begin to ask whether the abundance of such objects is higher than predicted. A single unusual galaxy can be treated as a rare outlier. A larger pattern begins to press more firmly against the model assumptions. At first, the tension often expresses itself through stellar mass estimates. Stellar mass refers to the total mass locked into stars in a galaxy. This quantity is not measured directly like the weight of a stone on a scale. It is inferred from the light a galaxy produces and from models of how stellar populations emit light at different ages and compositions. When some early Webb candidates are interpreted through these models, they appear to contain surprisingly large numbers of stars for such an early epoch. If those estimates are accurate, then a substantial amount of gas must have cooled and turned into stars very quickly. That does not violate known physics in a simple way, but it can seem faster or more efficient than many simulations had suggested. Brightness alone contributes to the same concern. A galaxy that shines strongly in the infrared at very high redshift may be undergoing intense star formation, may contain a large stellar population, or may be affected by lensing or other factors. But when several such objects appear in early data, astronomers begin to test whether their numbers fit comfortably within expected population counts. The tension is not only about individual galaxies seeming large, it is also about the apparent frequency of bright galaxies in the young universe. If too many luminous sources are found too early, then either the observations are being misread, or galaxy growth in that era proceeds more rapidly or differently than many models assumed. The appearance of maturity also contributes to the sense of strain. Some early galaxy candidates seem not only bright but relatively smooth or organized in outline. This visual impression can be misleading if taken too literally, because distance, image processing, and limited resolution all affect how a source looks. Even so, when combined with inferred mass and luminosity, the impression of development becomes part of the broader concern. A galaxy that appears compact, luminous, and settled at an early redshift invites the question of how much physical evolution has already taken place by the time its light is emitted. The standard picture expects rapid change in the young universe, but it also expects there to have been only limited time for repeated cycles of star formation, enrichment, and structural growth. This is where public language can become much stronger than scientific language. Headlines may say that galaxies are impossible, or that the early universe breaks the rules, or that a different cosmos must exist. The scientific literature is usually more restrained. It speaks of tension, discrepancy, model dependence, and possible revision. The difference matters. Attention is not a collapse. It is a sign that observed data and expected outcomes are not aligning as neatly as before. Sometimes such tension fades when measurements improve. Sometimes it leads to modest adjustments in assumptions. More rarely, it opens the way to deeper conceptual change. At this stage, the appearance of tension is real, but its meaning remains under investigation. Part of the strain arises because galaxy formation models already contain many moving parts. Simulations must describe dark matter halos, gas inflow, cooling, star formation efficiency, stellar feedback, dust, radiation, and merging histories. Small changes in one assumption can affect the predicted brightness and abundance of galaxies at high redshift. When Webb data seem difficult to fit, the problem may lie in those astrophysical details rather than in the larger cosmological framework. Yet from the point of view of first reaction, the distinction is not always obvious. What astronomers see is that some galaxies seem too impressive too early, and that perception creates the immediate sense that the timetable may be under pressure. The tension also depends on how early the galaxies truly are. A source placed at a very high redshift becomes more challenging because it is being seen at a younger age of the universe. If later spectroscopy lowers the redshift even modestly, the same galaxy may become much easier to understand. Time matters sharply in the early cosmos. A difference of a few 100 million years can greatly change how much growth is plausible. For this reason, the strongest tension often gathers around the most extreme distance estimates. These are also the cases where uncertainty can be greatest. The farther the source is placed, the stronger the challenge becomes, but also the more important it is to secure the measurement. Another part of the strain comes from expectations built through earlier observation. Before Webb, telescopes such as Hubble already hinted at early galaxies, but infrared reach and sensitivity were more limited. Many models were tuned against that earlier picture. Webb then opens a deeper window and reveals more candidates, some brighter and perhaps more numerous than anticipated. This does not mean the earlier work is wrong. It means the explored region of parameter space has widened. As the field moves into this newly observed territory, the familiar balance between model and evidence must be recalibrated. The tension appears precisely because the new instrument reaches a regime where prior expectations had not yet been fully tested by direct observation. At this stage, the scientific atmosphere becomes one of watchful pressure rather than sudden revolution. Researchers compare catalogues, refine photometry, seek spectroscopic confirmation, rerun simulations, and test alternative assumptions about stars, dust, and gas. The tension is productive because it directs attention to where the model is most vulnerable and where the data are most informative. It forces a closer examination of what early galaxies truly are and how confidently their properties can be known. In this region of the story, the challenge takes recognizable form. Some Webb galaxies seem to occupy the young universe with more light, more stars, and more apparent development than simple expectations had prepared astronomers to see. The standard picture remains in place, but it no longer feels entirely effortless at these earliest times. The pressure has not yet resolved into a clear conclusion. It gathers instead as a measured unease, shaped by brightness, abundance, and inferred mass. That unease becomes the reason for the next inward step, where the observations themselves must be examined more critically, and the possibility of misreading faint ancient light must be faced with full restraint. The closer astronomers move toward firm interpretation, the more the data demand caution. A faint early galaxy is not a finished fact when it first appears in a deep field image. It is a measured signal shaped by the telescope, the observing strategy, the detector response, the surrounding sky, and the methods used to separate source from background. By the time a galaxy candidate is described as distant, bright, or massive, it has already passed through many layers of analysis. Each layer is necessary, and each layer can introduce uncertainty. This does not make the result unreliable by default. It means that scientific restraint becomes part of the observation itself. One of the first sources of caution lies in photometric redshift estimation. When a galaxy is too faint for immediate secure spectroscopy, astronomers often rely on its brightness across multiple wavelength bands. A sharp drop in brightness at shorter wavelengths may indicate the absorption of light by hydrogen along the line of sight and can suggest a very high redshift. This technique is powerful and often successful, but it is not infallible. A nearer galaxy containing substantial dust can sometimes imitate the colors of a much more distant one. Dust absorbs and reddens light, changing the observed pattern across filters. If the source is faint and only weakly detected in some bands, the uncertainty grows. A candidate can move from a very early epoch to a later one if the color interpretation changes even modestly. Spectroscopy offers stronger confirmation, yet it also has limits. The distant galaxies of greatest interest are often extremely faint, and their spectra may contain only weak features. Sometimes an emission line appears clearly and fixes the redshift with confidence. At other times the spectrum is noisy, incomplete, or ambiguous. A line may be absent not because the galaxy is nearer, but because the line is weak, blocked, or beyond the useful range of the observation. In some cases, multiple spectral interpretations remain possible until additional data arrive. This means that even spectroscopy, though more secure than broad band color alone, can still leave room for care when dealing with the most distant and challenging sources. The measurement of brightness also carries uncertainty. Astronomers must decide how much light belongs to the source and how much comes from the background. In crowded deep fields, neighboring objects may overlap. A bright foreground galaxy can spill light into the region of a faint background source. Small errors in background subtraction can change the inferred brightness of an object near the detection limit, because brightness feeds directly into estimates of stellar mass and star formation activity. These small photometric uncertainties can grow into much larger uncertainties in physical interpretation. A galaxy that seems extraordinary at one measured brightness may seem much less so after a modest revision. Gravitational lensing introduces another layer of complexity. When a foreground cluster or massive galaxy bends and magnifies the light of a more distant source, the background object may appear brighter than it truly is in its unlensed state. This magnification is scientifically valuable because it brings faint galaxies into view, but it must be modeled carefully. If the amount of lensing is overestimated or underestimated, the intrinsic brightness and size of the background galaxy can be misjudged. In some fields, especially those built around strong lenses, this becomes a central issue. The telescope may see farther because of magnification, yet the very effect that reveals the galaxy can complicate the interpretation of its true physical scale. Selection effects also shape the sample. A telescope does not reveal all galaxies equally. It is more likely to detect sources that are brighter, more compact, or more favourably placed against the background. Deep surveys, therefore, do not provide a simple census of everything that exists in a given epoch. They provide a census filtered by detectability. This matters when astronomers ask whether luminous galaxies are unusually common in the early universe. The sample found by Webb is influenced by where the telescope looked, how deeply it looked, which filters were used, and which kinds of sources are easiest to distinguish. A population may appear richer in bright galaxies partly because faint diffuse galaxies remain below the threshold of detection. Cosmic variance adds a broader statistical caution. The universe is not perfectly uniform on smaller observational scales. One survey field may contain a local excess of galaxies, while another may be relatively sparse. When astronomers study small deep fields, they are sampling a limited part of the cosmic web. A region that happens to contain several luminous young galaxies may not represent the average conditions of the universe at that time. For this reason, results from one field gain strength when similar patterns appear in other independent fields. Until then, the possibility remains that some apparent abundance is partly a feature of where the telescope happened to look. Mass estimates are especially model dependent. A galaxy does not announce its stellar mass directly. Astronomers infer mass by comparing observed light with models of stellar populations. These models depend on assumptions about the ages of stars, the distribution of stellar masses at birth, the presence of dust, and the contribution of nebular emission from gas surrounding young stars. If a galaxy's light is dominated by a recent burst of star formation, it may appear brighter relative to its mass than a more settled stellar population would. In that case, a simple reading of brightness could exaggerate the amount of stellar material present. Conversely, dust and older stars can complicate the picture in other directions. The inferred mass is therefore never a simple translation from light to matter. The first wave of Webb results naturally attracts intense attention, and early interpretations can lean toward the striking edge of the data. This is not a failure of science, but part of its early movement. Initial catalogues identify candidate outliers. Follow-up observations then test whether those outliers remain extreme under closer examination. Some do, some become less dramatic. Some are replaced by better measured examples. Over time, the field shifts from first surprise to a more stable census. In that transition, caution acts as a corrective, not as a denial of discovery. It keeps the interpretation proportionate to the evidence. Observations already indicate that Webb has truly opened a deeper view of the early universe, and that luminous galaxies are present at unexpectedly early times in at least some cases. It remains uncertain, however, exactly how severe the tension is for the standard picture once redshifts, masses, dust, lensing, and sample biases are all treated with full care. That distinction is important. The existence of surprise is clearer than the final scale of the problem. Between the image and the theory lies a long chain of measurement, and each link must be tested. In this inward layer of the subject, caution becomes the governing method. The challenge posed by early Webb galaxies is real enough to merit serious study, but the data are subtle, and the interpretation depends on many technical decisions. Faint ancient light must be separated from noise, dust, overlap, magnification, and statistical bias before it can carry full theoretical weight. The result is not a retreat from discovery, it is a deepening of it. The more carefully the evidence is handled, the more clearly astronomers can tell whether the tension reflects a true need for new explanation, or a difficult but manageable revision within known astrophysics. Within the tension created by early Webb observations, astronomers first look for explanations that remain inside known physics, before any thought is given to a fundamentally different cosmos. The more careful scientific habit is to ask whether ordinary processes in early galaxies can account for what seems surprising. This inward step moves away from the first impression of galaxies that look too bright or too massive, and toward the physical mechanisms that might alter those impressions. The central idea is simple. A galaxy can appear more extreme than it truly is if its light is being produced or interpreted in ways that differ from the assumptions built into earlier models. One of the most widely studied possibilities is unusually intense star formation. In the early universe, gas is abundant, conditions are dense, and galaxies may convert available gas into stars with great efficiency during short active periods. If a galaxy is caught during one of these bursts, it can shine much more strongly than a quieter system of the same mass. A recent burst fills the galaxy with many young hot stars, and these stars emit large amounts of ultraviolet light. After cosmic redshift stretches that light into the infrared, the galaxy can appear remarkably luminous in Webb observations. In such a case, the brightness does not necessarily mean the galaxy has already built an enormous long-lived stellar population. It may instead reflect a brief but powerful phase of stellar production. Closely related to this is the effect of nebular emission. When young hot stars flood surrounding gas with energetic radiation, the gas responds by emitting its own light at characteristic wavelengths. This glowing gas can add significantly to the total signal recorded by the telescope. If that extra light is not fully accounted for, the galaxy may seem to contain more stars, and therefore more stellar mass, than it actually does. In the earliest analyses of Webb data, this effect becomes especially important because many distant galaxies are observed through broad filters rather than through complete detailed spectra. The measured brightness in a filter can contain a mixture of starlight and gas emission, and separating those contributions is not always easy. A galaxy that looks exceptionally massive may become more ordinary once strong nebular light is included properly in the model. The age of the stellar population also matters. A young stellar population produces more light per unit mass than an older one. This means that two galaxies with the same observed brightness can imply very different stellar masses depending on whether the stars are mostly young or have been shining for a longer time. If the earliest Webb galaxies are dominated by very recent star formation, then some first estimates of their masses may be too high. Brightness by itself does not tell whether a galaxy is large and mature or small, and caught in a vivid early phase. The difference depends on the history of star formation, and that history must be inferred from subtle patterns in the light. Dust introduces another possible adjustment. Dust is often thought of as something that merely blocks light, and in many cases it does. Yet dust can also reshape the observed spectrum in ways that complicate simple interpretation. It can redden a galaxy, making it resemble a more distant source or changing how its stellar population is modelled. Early galaxies may contain dust with properties different from those typical of better studied nearby systems. If the dust grains are larger, less processed, or distributed differently, then the relation between observed colour and true underlying stellar mass may shift. The light reaching Webb would then require different assumptions than those commonly used in earlier galaxy models. A galaxy might appear older or heavier than it really is if the dust correction is not well matched to early cosmic conditions. Another ordinary explanation involves active black holes. In some galaxies, gas may be falling onto a central black hole and heating strongly in the process. This activity can add substantial light, making the galaxy brighter than starlight alone would suggest. If the extra luminosity is attributed mainly to stars, the inferred stellar mass can be exaggerated. This possibility has gained attention because a growing black hole can mimic some of the brightness expected from a large stellar population. In the earliest universe, when galaxies are dense and gas-rich, black holes may grow rapidly in some systems. Their contribution need not dominate every source, but in a subset of bright early galaxies it could alter the balance between observed light and inferred mass. Merging also provides a natural explanation for some of the apparent excess. If two or more small galaxies are in the process of combining, their light may be measured together as though it comes from a single more massive object. At extreme distances, limited resolution can make closely spaced components difficult to distinguish. What looks like one luminous galaxy may partly be a crowded interaction region containing several young systems. Such blending would increase the apparent brightness and could produce the impression of unusually rapid growth. The early universe is expected to be rich in merging activity, so this explanation fits naturally within standard galaxy formation rather than challenging it. Changes in the assumed distribution of stellar birth masses may also matter. Astronomers often model stellar populations using an initial mass function, which describes how many small, medium, and large stars are formed. If the earliest galaxies produce relatively more massive stars than later galaxies do, then a given amount of stellar mass would generate more light. That would again reduce the need to infer unexpectedly heavy galaxies from their brightness alone. This idea remains uncertain, because the true distribution of stellar birth masses in the first generations of galaxies is still not securely known. Even so, it illustrates how a modest change in ordinary astrophysical assumptions can shift the interpretation without requiring a new cosmological framework. As data improve, some of these ordinary explanations begin to work together rather than separately. A galaxy might be undergoing a starburst, have strong nebular emission, contain some dust with unfamiliar properties, and host an accreting black hole all at once. In that case, its observed brightness becomes the combined result of several processes. Early simplified models may have treated such systems too gently, assuming more settled stellar populations or more familiar conditions. Webb is revealing galaxies in a regime where rapid formation, low metallicity, compact structure, and energetic gas can all overlap. The surprise then comes not from impossible physics, but from the fact that early galaxies may use ordinary physics in more intense combinations than many earlier models emphasized. This does not mean the tension vanishes completely. Some galaxies remain notable even after more careful modeling. Yet the general direction of current work shows that part of the apparent crisis can soften when ordinary astrophysical effects are treated more fully. Stellar masses can decrease. Brightness can be reassigned partly to gas or black hole activity. Colors can be understood differently once early dust and young stars are modeled more realistically. What first looked like a demand for radical revision may in some cases become a demand for better galaxy physics inside the existing cosmological picture. In this inward region, the discussion becomes more disciplined and more physical. The bright early galaxies seen by Webb need not point immediately toward a different universe. They may instead reveal that early galaxies are efficient, compact, chemically simple, and temporally brilliant in ways that make them easy to overread at first glance. Ordinary explanations remain powerful because the early cosmos is not quiet. It is active, gas-rich, and capable of producing bursts of light that complicate any direct translation from brightness to mass. The deeper astronomers move into the data, the more the question shifts from whether known physics fails to whether known physics has been modelled with enough intensity, enough realism, and enough care for the strange vigour of the first galaxies. At this point in the discussion, the phrase different universe begins to appear. not first in technical analysis, but in public interpretation. It arises when surprising observations are pulled away from their careful scientific setting and translated into larger, more dramatic language. A galaxy that seems unexpectedly bright at an early time becomes, in the public imagination, evidence that the whole universe may operate under different rules. A tension in galaxy formation becomes a hint of another cosmos. This shift in language is important because it marks the difference between what Webb actually observes and what some headlines suggest. The telescope records ancient light from distant galaxies. It does not photograph another universe. The idea of a different universe enters as an interpretation layered far above the data, and it must be examined with unusual care. In science, the word universe can be used in more than one way. Most often, it refers to the total physical cosmos that includes all matter, radiation, space, and time accessible to observation and theory. In other contexts, especially in theoretical discussion, the word may be extended to include separate domains, separate cosmic histories, or regions governed by different boundary conditions. These are not casual meanings. They arise from advanced attempts to understand inflation, quantum cosmology, or the mathematical structure of physical law. When public language says that Webb may have found a different universe, it often compresses several layers of meaning into one phrase and leaves out the distinctions that scientists rely on. The more careful statement is that unexpected observations can place pressure on a model. A model is a structured description of how some part of reality behaves. If observations and predictions do not align well, scientists may revise the parameters of the model, improve the treatment of known processes, or in more difficult cases reconsider deeper assumptions. None of these steps automatically implies a separate cosmos. A mismatch between Webb observations and simplified galaxy formation expectations is still a mismatch occurring inside the observed universe. It concerns how galaxies form, how light is interpreted, or how cosmic evolution is modeled. The leap from this to a truly different universe is not a direct inference. It is a speculative enlargement. The idea becomes more understandable when the standard cosmological picture is separated into layers. One layer concerns the broad expansion history of the cosmos, the growth of large-scale structure, and the role of dark matter and dark energy. Another layer concerns the astrophysics of galaxies, including star formation, dust, gas, feedback, and black hole growth. Many of the tensions raised by Webb belong most directly to the second layer. The early galaxies may be brighter, denser, or more efficient than expected, but that does not immediately threaten the broad existence of cosmic expansion, the general timeline of structure formation, or the overall framework supported by many other observations. It may instead mean that the details of early galaxy physics are more extreme than earlier models assumed. In that case, the universe is not different in its deepest structure. The description of one era within it is being refined. Even when scientists consider more fundamental possibilities, the language remains narrower than popular summaries suggest. A researcher might ask whether the expansion history at early times is being interpreted correctly, whether dark matter behaves exactly as assumed in current models, or whether some ingredient in the early cosmos changes the pace of galaxy formation. These are serious questions, but they are still questions about the workings of the same observable cosmos. A revised cosmology is not the same as evidence for another universe existing beside this one. The distinction matters because scientific reasoning moves by specific causal steps. Each step must be supported by evidence. The headline phrase often skips many of those steps and presents the most dramatic destination first. There is also a psychological reason the phrase different universe spreads so easily. The early universe is remote, difficult to imagine, and not directly accessible to everyday experience. When observations from that era seem surprising, the mind naturally reaches for large language. The greater the distance and the greater the age, the easier it becomes to treat the region as almost separate from the familiar cosmos. Yet the light web records comes from galaxies within the same continuous history that includes the Milky Way, the Earth, and the present day. The early universe is strange, but it is not foreign in the sense of being outside known existence. It is an earlier condition of the same expanding reality. Some interpretations push the phrase further by suggesting that if early galaxies seem to mature too soon, then perhaps time itself worked differently, or perhaps some hidden sector of reality influenced structure formation in ways beyond the standard picture. These are not impossible questions to ask in principle, but they remain far beyond what the Webb data alone can demonstrate. Observations indicate that Webb is revealing a richer and sometimes more challenging early galaxy population than many had anticipated. It remains uncertain whether this requires only improved astrophysics, a moderate cosmological adjustment, or something deeper. The crucial point is that uncertainty should not be filled with the dramatic conclusion before the chain of evidence is strong enough to support it. The phrase other universe can also mislead because it suggests direct detection of a separate world, as though one could point to a distant red galaxy and say that it belongs elsewhere. Webb does not work in that way. Every source it observes lies along lines of sight within the observable sky, and is interpreted through the physics of light, spectra, redshift, and structure formation. If a galaxy is unexpectedly bright, that is a challenge in interpretation, not a label that places the galaxy outside the universe. Even the most distant galaxies known are still part of the cosmic history that standard astronomy attempts to trace from early times to the present. In scientific practice, the right response to such language is not dismissal but narrowing. One asks what is actually claimed, what data support the claim, what assumptions link the data to the interpretation, and whether simpler explanations have been explored. When this narrowing is applied to the strongest statements about a different universe, the claim usually softens. What remains is not proof of another cosmos, but a discussion about whether certain galaxies are harder to explain than expected. That may still be important. It may even prove historically significant, but it is not the same thing as observational evidence that a separate universe exists. In this region of the subject, the dramatic phrase is brought inward and reduced to its scientific core. Webb's observations can challenge assumptions, strengthen alternatives, and force revisions in the story of early galaxy growth. They can make the familiar cosmic picture feel less settled at certain points. What they do not do, at least by themselves, is establish that a different universe has been seen. The phrase survives because it captures public imagination, but under careful examination it becomes a metaphor for interpretive strain rather than a literal conclusion. The deeper one moves into the evidence, the more the headline dissolves, leaving behind a quieter and more disciplined question about how far current models can stretch before they need to change. Beyond the immediate question of early galaxies lies a broader territory of ideas that often gathers under the word multiverse. This word does not refer to one single theory. It is a label applied to several different kinds of proposals about reality on scales far beyond direct observation. Some versions arise from inflationary cosmology, which is the idea that the young universe undergoes an extremely rapid expansion in its earliest fraction of a second. Other versions arise from attempts to interpret quantum mechanics, the theory that describes matter and energy at very small scales. Still others appear in speculative extensions of fundamental physics. These ideas are not all the same, and they do not all make the same claims. Because of that, the first requirement of clarity is to separate them before asking whether Webb has anything meaningful to say about them. One of the most commonly discussed multiverse concepts comes from eternal inflation. In ordinary inflationary cosmology, the early universe expands with extraordinary speed for a brief period, smoothing and stretching space while amplifying tiny quantum fluctuations that later grow into cosmic structure. In some theoretical versions, inflation does not end everywhere at once. Instead, it continues in some regions while stopping in others, where it stops. A region like the observable universe can form, with particles, radiation, galaxies, and the long subsequent history of cosmic evolution, where it continues. More such regions may eventually emerge. The result is a picture in which many separate cosmic domains could exist, each effectively cut off from the others by ongoing expansion. This is one major source of multiverse discussion in modern cosmology. Another class of multiverse ideas enters through quantum theory. Some interpretations of quantum mechanics attempt to account for the apparent branching of possible outcomes by treating all outcomes as real in different branches of a larger quantum state. In popular language, this is often described as many worlds. The concept is not about distant galaxies or early cosmic structure in the first place. It concerns the interpretation of measurement and the mathematical development of quantum states. Even when discussed seriously, it belongs to a very different conceptual layer from Webb observations of ancient galaxies. It is a proposal about how physical outcomes are understood at the foundational level, not a prediction that a space telescope should directly observe a neighboring universe through deep field imaging. There are also speculative ideas involving extra dimensions, landscape models in high-energy theory, or separate cosmic histories emerging from different vacuum states. In some of these proposals, physical constants or particle properties could differ from one domain to another. Such concepts can be mathematically rich, but they are difficult to test directly. Their relationship to observation is often indirect and model-dependent. A theory may allow multiple possible universes in principle, without providing a clean observational signature that can be searched for in current data. This is one reason multiverse concepts remain scientifically delicate. They can emerge naturally from some theoretical frameworks, yet their empirical status is often much weaker than that of the observations used to motivate everyday cosmology. Inflation itself occupies a more grounded position than the broader multiverse ideas built from it. Inflation is not directly seen in the same way a galaxy is seen, but it helps explain several observed features of the cosmos, including the large-scale smoothness of the universe and the origin of the small fluctuations that later become galaxies and clusters. These fluctuations leave an imprint in the cosmic microwave background and in the large-scale structure of matter. In that sense, inflation stands closer to established cosmology than the more elaborate picture of eternally self-reproducing cosmic domains. The step from inflation to multiverse is therefore not automatic. Some inflationary models suggest it, others do not require it in the same form. Public discussion often compresses this distinction and treats inflation and multiverse as though they were one idea, but scientifically they must be kept apart. Once these concepts are separated, the role of Webb becomes easier to define. Webb observes distant galaxies, their light, their spectra, their chemical signatures, and their place in early cosmic time. It can test models of galaxy formation, constrain the timing of chemical enrichment, and refine the picture of how quickly stars and structures emerge after the beginning of cosmic expansion. These are powerful achievements, but they do not amount to direct observation of inflationary bubbles, quantum branches, or alternate physical domains. Webb's data can affect the plausibility of some cosmological models at the margins by changing what must be explained in the early universe. Yet this is still a long way from turning multiverse concepts into observed facts. This distinction matters because a strained astrophysical model can tempt the imagination toward the most dramatic available explanation. If galaxies seem too bright too soon, one might be tempted to think that the whole cosmic setting must be radically different. But multiverse proposals do not function as a simple repair tool for every observational tension. They are large frameworks with their own assumptions and their own evidential burdens. A surprising galaxy does not naturally point to quantum branching, and a refined estimate of early star formation does not directly test whether inflation produces multiple disconnected domains. The path from Webb data to multiverse claims is therefore long, indirect, and full of theoretical choices. Observations indicate that Webb is revealing early galaxies with properties rich enough to sharpen cosmological questions. It remains uncertain whether any of these questions will eventually push theorists toward more fundamental revisions in the broad story of the early cosmos. Even if that happens, the presence of a fundamental revision would still not by itself prove a multiverse. Scientific explanations usually move inward by stages. First the data are checked, then the astrophysics is refined, then the cosmological assumptions are tested. Only much later, if simpler frameworks fail repeatedly and systematically, do more radical theories gain stronger motivation. The multiverse belongs to that far inner edge of speculation, not to the first response to an observational anomaly. There is also an important difference between explanatory possibility and evidential support. A theory may be able to include many possible universes, but this does not mean current observations favour that theory over simpler alternatives. Webb's discoveries can enrich the conversation by revealing how active, luminous, and chemically interesting the early universe is. They can narrow which models of early structure formation remain plausible. They can even make some inflationary or high-energy scenarios more attractive than others, if those scenarios better accommodate the new constraints. Yet all of this remains within the realm of indirect inference. The telescope is not opening a window onto parallel cosmic worlds. It is refining knowledge of this one. In this region of the story, the word multiverse settles into its proper scale. It becomes not a conclusion drawn from Webb, but a family of theoretical ideas that live far deeper inside speculative cosmology than public language usually admits. Some are connected to inflation, some to quantum interpretation, some to high-energy theory, and all of them stand at a significant distance from direct telescope evidence. Webb can sharpen the questions cosmologists ask about the early universe, and in that indirect sense it can influence the broader background against which multiverse ideas are judged. But the influence is distant and mediated, not immediate and decisive. The early galaxies Webb sees belong to the observable cosmos, and the multiverse remains a theoretical horizon beyond them, still uncertain, still debated, and still far from observational confirmation. When attention returns from broad theoretical ideas to the direct work of the telescope, the role of Webb becomes more precise. It does not search for separate universes or test speculative frameworks in isolation. It measures light from specific objects and uses those measurements to refine knowledge of the early stages of cosmic structure. The strength of Webb lies in its ability to gather faint infrared signals, resolve distant sources, and separate light into detailed spectra. Through these methods, it places constraints on what the early universe contains and how it behaves. These constraints act as boundaries within which cosmological theories must operate. They do not by themselves create new universes. They narrow the range of acceptable descriptions for this one. One of the most important areas Webb tests is the timeline of star formation. By observing galaxies at high redshift and analyzing their light, astronomers estimate how quickly stars begin to form after the initial expansion of the universe. The presence of luminous galaxies at early times indicates that star formation is already active, perhaps more active than expected in some models. Spectral measurements can reveal the presence of ionized gas, the intensity of radiation from young stars, and the relative contributions of different stellar populations. These details allow astronomers to move beyond simple brightness and into a more physical description of early galaxies. If star formation begins earlier or proceeds more efficiently than previously modeled, the timeline of galaxy growth must be adjusted accordingly. Chemical enrichment is another key test. The earliest matter in the universe is composed primarily of hydrogen and helium. Heavier elements are created within stars and distributed through stellar winds and explosive events. By examining spectral features, Webb can detect elements such as oxygen, carbon, and nitrogen in distant galaxies. The presence and relative abundance of these elements provide clues about how many generations of stars have already formed and died by the time the observed light is emitted. If a galaxy shows signs of significant chemical enrichment at an early epoch, it suggests that stellar processes have already progressed rapidly. This does not imply a different universe, but it does inform how quickly ordinary processes operate in the young cosmos. Dust is also revealed through Webb's measurements. Dust forms from heavier elements and affects how light is absorbed and re-emitted. By studying infrared emission and absorption patterns, astronomers can estimate the amount and nature of dust in early galaxies. This information feeds back into models of star formation and galaxy evolution, because dust influences cooling, radiation transfer, and the visibility of stellar populations. Early results indicate that dust may be present in some galaxies sooner than simple models had suggested. This again points toward rapid development under certain conditions, not toward a separate physical domain. Webb also contributes to the study of galaxy structure at early times. Although the most distant galaxies remain small and faint, improved resolution allows astronomers to examine whether they are compact, clumpy, or interacting. Patterns of structure provide clues about how matter is assembling. A clumpy appearance may indicate regions of active star formation within a turbulent gas environment. A more compact form may suggest rapid central accumulation of material. Interactions between nearby galaxies can be identified when shapes appear distorted, or when multiple components are seen close together. These structural observations help refine models of how galaxies grow through merging and internal processes. Another area of measurement involves the intergalactic medium, the diffuse gas that lies between galaxies. In the early universe, this gas transitions from a neutral state to an ionized one in a process known as reionization. The timing and progression of this transition can be studied through the absorption of light from distant sources. Webb contributes by identifying galaxies that may be responsible for producing the radiation that drives this change. The number and brightness of early galaxies affect how quickly reionization can occur. If galaxies are more numerous or more luminous than expected, they may play a larger role in shaping the state of intergalactic gas. All of these measurements function as constraints. A constraint does not dictate one single theory. It rules out certain possibilities and supports others. For example, if Webb finds that early galaxies are consistently more luminous than predicted by a given model, that model must be revised or replaced. If chemical enrichment appears earlier than expected, then star formation and stellar evolution must be adjusted within the model. Each observation reduces the space of acceptable explanations. Over time, the accumulation of such constraints leads to a more accurate and detailed understanding of cosmic history. The process is gradual. Early results from Webb provide initial constraints that are often broad and uncertain. As more data are collected, repeated observations improve signal quality and reduce noise. Spectroscopic confirmations replace tentative photometric estimates. Larger surveys increase sample size and reduce the influence of cosmic variance. With each step, the picture becomes more stable. Some early surprises remain. Others diminish as measurements improve. The goal is not to preserve the initial sense of shock, but to replace it with a clear and consistent account of what the data truly show. In this setting, Webb acts as a refining instrument rather than a revolutionary one in the dramatic sense. It deepens the reach of observation and sharpens the clarity of early cosmic conditions. It tests how well existing theories perform under new evidence. If those theories need adjustment, Webb helps guide that process. If deeper revisions are required, they will emerge through sustained tension across many lines of evidence, not from a single observation or a brief period of unexpected results. The language of a different universe does not belong naturally in this domain. Webb's measurements remain anchored in the observable cosmos, in the behavior of light, matter, and gravity as currently understood. They may challenge the details of how galaxies form and evolve, and they may influence how cosmologists think about the earlier stages of expansion. Yet all of this takes place within the same continuous physical framework. The telescope is not stepping outside that framework. It is illuminating regions of it that were previously dim. In this region of the narrative, the focus narrows to what Webb actually tests. It measures star formation, chemical enrichment, dust, structure, and the state of intergalactic gas. Each of these measurements feeds into a network of models that describe the early universe. The constraints grow tighter, the uncertainties become more defined, and the interpretation becomes more grounded. The early attention is not ignored, it is absorbed into a process of refinement. The result is a clearer understanding of where knowledge is strong, where it is incomplete, and how far the current picture can be extended before it must be reshaped. At the core of the present discussion lies uncertainty, not as a weakness to be hidden, but as the true shape of the frontier. By the time the story reaches this inward point, the outer layers have been stripped away. The dramatic headline has been reduced. The first visual surprise of bright early galaxies has been tested against redshift, measurement limits, dust, gas emission, stellar population models, and the wider structure of accepted cosmology. What remains is a quieter but more difficult question. After all known cautions and ordinary explanations are taken seriously, how much of the tension truly endures, and what kind of revision, if any, does it require? One source of uncertainty lies in the redshifts themselves. Although Webb has greatly improved access to very distant galaxies, not every important source has a definitive spectroscopic redshift. Some galaxies still rely mainly on photometric estimates, and those estimates, while often strong, are not equally secure in every case. A modest change in redshift can shift a galaxy from an extremely early epoch to a somewhat later one, and that change can alter the theoretical pressure considerably. In the young universe, time is dense with consequence. A difference of even a relatively short interval can allow substantially more star formation, more chemical enrichment, and more structural development than a more extreme interpretation would permit. Because of this, uncertainty in distance becomes uncertainty in the severity of the challenge. Another uncertainty lies in how light is converted into physical properties. Brightness is observed, stellar mass is inferred, star formation history is inferred, dust content is inferred, The presence of strong gas emission may be measured directly in some cases, but in many others it is estimated through models fitted to limited data. The model assumptions matter deeply. If the stellar populations are younger than assumed, the inferred masses may drop. If nebular emission is stronger, some of the brightness may belong to gas rather than stars. If dust behaves differently in the early universe than in nearby galaxies, color-based interpretations may shift. These uncertainties do not erase the data, but they widen the range of meanings the data can carry. There is also uncertainty in the simulations used for comparison. Cosmological simulations and galaxy formation models have become highly sophisticated, yet they still depend on subgrid prescriptions, which are simplified descriptions of physical processes too small or too complex to model directly in full detail. Star formation, supernova feedback, black hole growth, radiation transport, and turbulent gas behavior all involve assumptions. When observers compare Webb galaxies with theoretical expectations, they are not comparing them with a perfect forecast generated from first principles alone. They're comparing them with a framework that includes many informed but incomplete approximations. This means an apparent discrepancy may reflect a real challenge in nature, or it may reflect the limits of how current simulations represent early galaxy physics. Sample size remains another important issue. Although Webb has already produced remarkable surveys, the earliest and most extreme galaxy candidates still form a relatively limited set. Some fields are very deep but narrow, some are affected by lensing, some sample regions of the sky that may not be fully representative of average cosmic conditions. As more observations accumulate across more independent fields, the emerging population statistics may grow more stable. For now, part of the uncertainty lies in whether the most striking sources are rare but real extremes, or whether they indicate a broader population that is genuinely more luminous and more common than previous models expected. Until the census becomes fuller, interpretation remains provisional. The chemical state of the earliest galaxies also remains partly uncertain. Webb can detect evidence of heavy elements in some distant systems, yet the full pace of enrichment across the earliest epochs is still being mapped. It is not yet completely settled how quickly the first generations of stars enrich their surroundings, how efficiently dust forms in those conditions, or how these processes vary from one environment to another. Since chemistry affects cooling, star formation, opacity, and emitted light, uncertainty in early chemical evolution spreads into uncertainty about galaxy appearance and growth. What seems surprisingly mature may partly reflect rapid local enrichment, rather than a wholesale failure of the broader timeline. Another open question concerns the first stars themselves. The earliest generations of stars likely form under conditions different from those found in later galaxies. Their typical masses, lifetimes, and radiation output may not match the assumptions built from better understood nearby stellar populations. If the first stars are, on average, more massive or more efficient at producing intense radiation, then early galaxies could appear brighter for a given total stellar mass. This would ease some of the tension without requiring a new cosmological framework. Yet the exact properties of these first stellar generations remain difficult to observe directly, and so they remain an inward source of uncertainty in the interpretation of Webb's most distant galaxies. The role of black holes also remains incompletely known. If some early galaxies host rapidly growing black holes, those black holes may add substantial luminosity and alter surrounding gas conditions. In some cases, this could make a galaxy seem more developed or more massive than it is when interpreted through starlight alone. Webb is beginning to identify active black hole candidates at high redshift, but the frequency, growth rates, and influence of such objects in the earliest galaxy population are still under study. This means that some portion of the observed tension may eventually be redistributed into a better understanding of early black hole activity. At the most inward level, the uncertainty concerns not only specific galaxies, but the balance between two broad possibilities. One possibility is that the standard cosmological framework remains sound, and the tension arises mainly because early galaxy astrophysics is more efficient, burst-driven, and observationally subtle than models had captured. The other possibility is that, after enough careful revision, a deeper mismatch remains that points toward a need for more fundamental adjustment in the cosmological story itself. Observations indicate that the first possibility currently remains strong and often sufficient in many cases. It remains uncertain, however, whether it will explain the full population of the most challenging sources as the data improve. This is the natural condition of science at a living frontier. Certainty does not vanish everywhere. Much is already well established. The universe expands. Early galaxies exist. Webb is observing them with extraordinary power. Some appear surprisingly luminous at early times, yet the final meaning of that surprise is not settled. There is no clear evidence that another universe has been detected. There is also no reason to dismiss the tension as empty noise. Instead, the field now rests in a narrow space between premature drama and premature closure. In this inner region, uncertainty becomes the most honest conclusion. The early galaxies seen by Webb have not overturned cosmology, but they have sharpened the places where cosmology and galaxy formation theory must work hardest. The measurements are real, the caution is necessary, and the final balance between revision and continuity remains open. Science does not hurry this stage. It allows uncertainty to remain where evidence is still incomplete. And in that restraint, the deepest discipline of the subject becomes visible. The question is no longer whether surprise exists. The question is how much of it will remain after the evidence has fully settled into place. At the innermost layer of the subject, the focus settles not on distant galaxies themselves, nor on instruments, nor on speculative extensions of theory, but on the method by which knowledge is formed and revised. The quiet pattern that emerges from the Webb observations is not one of sudden replacement, but of gradual adjustment guided by evidence. The early universe, as revealed through faint infrared light, does not present a final answer. It presents a series of measurements that must be interpreted within a disciplined framework. This framework allows for change, but it requires that change to proceed step by step, with each conclusion anchored in what can be reliably known. The first element of this method is patience. Observations accumulate over time. Initial deep fields provide a glimpse, but they are followed by broader surveys, repeated exposures, and more precise measurements. Spectroscopic confirmation strengthens or revises early distance estimates. Improved data processing reduces noise and clarifies faint structures. Each stage refines the picture. A galaxy that appears extraordinary in early analysis may become more ordinary as its properties are measured more carefully. Another may remain unusual and draw increased attention. The overall understanding does not move in a single leap. It evolves through accumulation and correction. The second element is comparison. No observation stands alone. Each galaxy is considered within a population, each population within a model, and each model within a broader theoretical context. If one source appears too bright for its estimated age, astronomers ask how many similar sources exist, how they are distributed across different fields, and whether their properties align with variations already allowed by the model. A single anomaly is treated differently from a consistent pattern. Over time, Patterns become clearer as sample sizes increase and observational biases are better understood. This comparative approach prevents early impressions from dominating interpretation. The third element is revision within continuity. Scientific models are not rigid structures. They are designed to be updated as new data become available. When Webb reveals early galaxies that seem more luminous or more numerous than expected, the first response is not to discard the entire cosmological framework. It is to examine where the framework may need adjustment. This may involve refining assumptions about star formation efficiency, dust behavior, stellar populations, or the role of black holes. If such adjustments bring the model into better agreement with observation, then the continuity of the broader theory is preserved while its details become more accurate. The fourth element is proportional response. The scale of a conclusion must match the strength of the evidence. Webb has provided strong evidence that early galaxies can be bright, active, and in some cases more developed than earlier simplified expectations suggested. It has not provided direct evidence of a separate universe or of a complete breakdown in the laws of physics. Maintaining proportionality ensures that interpretation does not outrun data. It allows the field to remain grounded even when observations are surprising. This discipline is not a limitation. It is the mechanism by which reliable knowledge is built. The fifth element is openness to deeper change if required. While the standard cosmological model remains strongly supported by a wide range of observations, it is not treated as unchangeable. If repeated, well-confirmed observations consistently resist explanation within the current framework. Then more fundamental revisions can be considered. This process is slow because the threshold for such change is high. It requires convergence across multiple lines of evidence, not a single class of objects or a single observational technique. Webb contributes to this process by extending the reach of observation into earlier times, where the model is less directly tested. If a deeper mismatch exists, it will become clearer through sustained study, not through immediate declaration. In this quiet center, the meaning of Webb's discoveries becomes clearer. The telescope has not uncovered a different universe in the literal sense. It has uncovered a more detailed and sometimes more demanding view of the early stages of this universe. It has revealed galaxies that form stars efficiently, that can appear bright even at great distances, and that may develop structure and chemical complexity sooner than many models had emphasized. These findings enrich the understanding of cosmic history. They sharpen the questions that astronomers ask about how matter gathers, how stars ignite, and how galaxies take shape. The idea of a different universe, when translated into this disciplined setting, becomes a reflection of the human response to surprise rather than a direct conclusion from data. It expresses the sense that something familiar has become less certain. Yet the scientific process transforms that feeling into specific, testable questions. How accurate are the redshifts of the most distant galaxies? How reliable are the inferred stellar masses? How significant is nebular emission in shaping observed brightness? How rapidly can gas convert into stars under early conditions? How do black holes contribute to early luminosity? Each question narrows the scope of uncertainty and moves the field closer to a stable understanding. As observations continue, the early tension may resolve in several ways. It may diminish as measurements become more precise and models more realistic. It may persist in a limited form, leading to targeted adjustments in astrophysical assumptions. In a less likely but still open possibility, it may reveal a deeper issue that requires broader revision in cosmology. At present, observations indicate that the first path is already active in many cases. with ordinary processes explaining part of the apparent excess. It remains uncertain whether this will be sufficient in all cases as the data expand. The inward journey thus ends not with a dramatic conclusion but with a balanced view. Webb has extended vision into a region of cosmic history that was previously only partly known. In doing so, it has made the early universe more vivid and more complex. It has shown that even well-established models must be tested continually against new evidence. It has also shown that surprise does not automatically imply radical change. Instead, it invites careful measurement, thoughtful interpretation, and steady refinement. In this final region, the subject returns to stillness. The distant galaxies remain as faint sources of stretched light. The telescope continues its quiet work in cold orbit. The models of cosmology and galaxy formation remain in motion, adjusting where needed and holding where supported. The question of a different universe softens into a deeper appreciation of how knowledge grows. It grows not by sudden replacement, but by persistent attention to evidence, by the willingness to revise, and by the patience to let uncertainty resolve in its own time. The light from distant galaxies fades gently into the background of the wider sky, and with it the urgency of interpretation softens. What remains is a quiet sense of scale and distance, where each faint signal carries a long history without needing to resolve every question it raises. The early universe, as seen through careful observation, becomes less a place of sudden disruption and more a gradual unfolding of structure, shaped by processes that are still being understood in detail. The telescope continues to collect light without urgency. Its mirrors remain aligned, its instruments remain cold, and its orbit remains steady. Each new observation adds a small piece to a larger pattern, one that does not demand immediate conclusion. In this slow accumulation, uncertainty is not an obstacle but a natural state. It allows knowledge to remain open, to adjust, and to settle only when the evidence becomes clear enough to support it. The galaxies themselves remain distant and quiet. Their light has travelled across expanding space, stretched and softened, carrying only what it can preserve. Some appear brighter than expected, some more structured, some more active, yet each one belongs to the same continuous history, a history that extends from the earliest moments of cosmic expansion to the present. There is no boundary crossed in their observation, only a deeper reach into what has always been there. The idea of another universe, once vivid at the surface, becomes less distinct here. It dissolves into a broader awareness that the known cosmos is still being explored in layers. What seemed at first like a break in understanding becomes part of a slower adjustment, where models are refined and assumptions are tested. The unknown remains, but it no longer presses outward with urgency. It settles inward as something to be approached with patience. In the quiet of this final view, the work of observation continues without interruption. Light arrives, instruments record, and interpretation follows at its own pace. The universe does not rush to explain itself. It offers its signals gradually, across vast distances and long intervals of time. In that steady offering, the search for meaning becomes calm, measured, and unhurried.